Phase-changing materials are a new class of compounds that absorb a significant amount of heat upon melting. The heat is safely stored without any loss until the temperature drops below the melting point. At this stage, the heat is released back into the environment. This property makes these materials very attractive for cooling and heating buildings. The access to Gaudi through the Australasian Leadership Computer Grants will enable us to perform one-of-a-kind calculations that will undoubtedly be the largest first-principle calculations ever performed in Australia.
Our project is focused on building a new generation of electronic devices based on organic molecules. Organic electronic materials have the potential to really transform the way that we make and use consumer electronics. From flexible display screens to solar cells, which are just so light that they could be incorporated into our clothing or even used to coat the wings of aircraft to provide power. So the key questions that we're wanting to address is why do devices have different properties depending upon the way that they're manufactured, and can we predict the behaviour of specific molecules in order to be able to make better and more reliable devices. Now, such calculations are enormous, and they're really only possible if we have access to the types of facilities which Gaudi and NCI are able to provide.
We're delighted about this ALCG grant, which will allow us to better understand the inner workings of supernova explosions. Supernovae are extremely powerful explosions of massive stars. For several weeks, they can be so bright as to outshine an entire galaxy. But we cannot look inside these explosions with our telescopes to figure out how they work. For that, we need supercomputers like Gaudi. We can already simulate supernova explosions quite decently, but to obtain really accurate models, we need to better resolve the delicate structures in the turbulent flow behind the shockwave of the explosion. And we need to put in more and more detailed physics into them. For example, because the interior of the star consists of ionized plasma, we can have very strong magnetic fields in there that affect the explosion. Our high-resolution simulations on Gaudi will allow us to much better understand how these phenomena play together and how supernova explosions are energized.
We all know of the huge impact that COVID-19 has had on our society. So how do we prevent another pandemic like this happening again? Well, COVID-19 is a coronavirus disease that emerged from animals. And in fact, there's hundreds of different coronaviruses circulating amongst bats, rodents, and other animals today. This project will help identify which of those viruses could be very dangerous to humans, and which ones could seed another pandemic. Over the last year, we've been using the resources of the National Computational Infrastructure to better understand how the coronavirus responsible for COVID-19 invades human cells using its famous spike protein. The huge new allocation in this grant will allow us to study not just one coronavirus, but a huge number of those coronaviruses that are out there amongst animals, so that we can identify which ones of those could be deadly to humans. We can also try to understand the patterns that make them so dangerous to more easily detect dangerous viruses in the future. This information can help us to monitor and isolate such viruses, as well as to prepare for them and prevent another pandemic occurring in the future.
My colleagues and I are very excited to have been awarded an Australasian Leadership Computing Grant to undertake a high-fidelity direct numerical simulation of a turbulent thermal boundary layer as an analog for a bushfire simulation. The overarching goal of our project is to simulate the complex interactions between fuel sources with different properties and the atmospheric turbulent boundary layer during bushfires. The advent and availability of high-performance computers like Gaudi is enabling detailed, physically accurate information about the process occurring in and around the bushfires to be obtained, and will allow us to develop improved fire-spreading models, evaluate available large eddy simulation models, and develop new models based on the findings of the study. And furthermore, allow us to develop high-fidelity, reduced-order models with fast yet accurate predictive capability.